The Kramers model, as just described, is really very limited because very few chemical reactions proceed through just one transition state. An exception might be the so-called unimolecular reaction, illustrated at the bottom of this slide by the isomerism of isonitrile, where the nitrogen and the carbon change positions. It's not a very good pedagogical example because one is left wondering about the valence of the carbon and nitrogen in this rather complex process, but nonetheless it does correspond quite well to this energy diagram in the Kramers model, where we have the isonitrile in the state E1 being converted to the state E2, and doing that at some rate K plus. E2 is converting back again to E1 at some rate K minus. So the rate of accumulation or loss of E1, where these square brackets mean concentration, is given by the rate at which it is lost, so that's minus K plus times the concentration of E1, plus the rate at which it is gained, so that is K minus times the concentration of E2. In equilibrium, the concentration of the reactants and products will not change, and so from that then we can say in equilibrium E2 over E1 is equal to K plus over K minus. This ratio of concentrations, or of rates, is called the equilibrium constant for the reaction. Recognizing that in equilibrium the ratio of populations of these states will be given by a Boltzmann factor as controlled in equilibrium now by this difference in free energy between the reactants and products, we can write that K equilibrium is equal to e to the minus delta G over RT. Remember that for a favored reaction, delta G is negative, and this means then if the reaction is strongly favored, this is the exponential of a large number, so K equilibrium is a large number. And most of the system of reactions and products will be found as product, if that indeed is the case. Let's turn now to the somewhat more interesting case of bimolecular interactions. These do not have to be controlled by a single intermediate step, but if they are, we can write down similar rate equations. So let's take a simple bimolecular interaction in which two protons come together to form a hydrogen molecule. So this is A plus B goes to C. And then by arguments just like the one on the last slide, we can define the equilibrium constant as the ratio of the product to the reactants. At this point, a comment on the units used. The equilibrium constant is dimensionless, and the reason for this is that the concentrations are expressed as activities, that is, concentration relative to some standard concentration. This exponential, of course, has to give a dimensionless number. It's just a ratio of populations. And so, for this reason, the units must be dimensionless. Even if the reaction is controlled by one step, other complications exist because usually reactions occur by some multiple of molecules interacting with one another, as in this reaction here. Please do exercise 315 at the back of the book, where you will see the result is that in this case we would write the reaction constant as The whole science of fitting reaction rates in multi-step processes is really quite complex, and I urge you to look at the beautiful book by Alan Furst that is reference 8 in chapter 3.